Right. Previously, we have examined how a system response can be in relation to its transfer functions and in relation to its input. And when we look at the transfer functions, we also looked in details how the poles of a system affect the performances, the rise time, the overshoot, and things like that. And we also discussed the closed loop systems, how to find the transfer functions of a closed loop system, and how controller, if we know the controller, how the controller changes the poles for the closed loop system to affect the performances or the responses of the system. Today, I'm going to talk about one of the design issues. That's to really try to see how we can actually use particular techniques to help us and tune the control parameters. Not that we assume we know them, we don't know them. But if we don't know them, how we can tune the controller to give us the responses we want through the location of the poles. The RootLocus design is one of the classic approach for control design, and it only affects one control parameter at a time. So we really can only tune one control parameter in the controller. It is a technique to study how the closed poles can be moved by the control gain k, that's a scalar value, from open loop transfer function and poles and zeros. And in that technique, we don't need to derive the closed loop transfer function and then try different values of k as we did before. But what we do here is to say, right, if I know the open loop transfer function of the plant and I want to tune a controller and how the closed loop poles can change with different values, and can we actually find all the possible closed loop poles without deriving the closed loop transfer function? This is what we do. Okay, because we are only dealing with one control gain at a time. So for this part of design, what we would do is we can, if there was dynamic part of the controller, we can move that together with the plant, assuming we know this already. The design of a dynamic controller or the dynamic part of the controller is a separate subject topic to discuss, which we will cover later on in your course. So if you look at the block diagram at the bottom, what we have here is a QS. QS is a transfer function that combines the controller or the dynamic part of the controller and the transfer function of the plant. The aim here is to see if that small k, i.e. it's a scalar, it's a number, if that k changes for all sorts of possible values from 0 to infinite, how the closed loop poles will move about without actually every time we derive the closed loop transfer function and then find the poles through different k values. So we want to find a way that will give us all the possible closed loop poles corresponding to different k values without finding the closed loop transfer function first. Okay, so there's a particular technique for that, which is called the RootLocus design technique. Okay, so we will work on that basis, trying to work out the k value and the relationship to the closed loop poles. The open loop transfer function is fixed. Okay, so we're not going to try to change any of that. So I'm copying that over from previous slide, the block diagram. Let's assume the plant QS has a transfer function of BS over AS. Okay, BS is the coefficient, represent the numerator terms in the transfer function. AS represent the denominator terms in the open loop transfer function. Now, if I use this to derive the closed-loop transfer function, what I get is k times q for the numerator, because that's in the forward path from R to Y. In the denominator, it's a 1 plus all the terms in the feedback loop. There are only 2 terms there. There's a small k, there's qs. So I'm going to substitute this into here, k times q plus 1. If I substitute equation 1 into equation 2, this becomes b over a, this becomes b over a. If I multiply a to the numerator and the denominator, I get k times bs divided by as plus kbs. K is a parameter for the control that we're trying to see its effect on the closed loop poles. Okay. Now, for the open loop transfer function, Qs equals to Bs over As. If I equate the numerator terms to 0, find the solutions, it will give me the open loop zeros. So Bs equal to 0 will give me the open loop zeros. If I equate the denominator terms of Qs to 0, that's As equals to 0, the solution of that equation will give me the open loop poles. So Bs equal to 0 give me open loop zeros, As equal to 0 give me the open loop poles. Now on the right hand side, I have the closed loop transfer function. Again, if I equate numerator terms to 0, that's k times Bs equal to 0. K is a constant, so it's the same as Bs equal to 0. That will give me equation number 3. Okay, now if you look at equation number 3 and compare that with equation number 1, they are the same. So what we have here is a situation where the closed loop zeros will be the same as open loop zeros. So this particular design method, looking at single control gain, does not change zeros. Okay, the closed loop zeros will be the same as open loop zeros. But if I equate the denominator term of Ts, which is As plus Kb, equal to 0, the solution of that, as shown in equation 4, okay, the equation is given in equation 4, the solution of that will give me the closed loop poles. Now, open loop poles will be the solution of As equal to 0. Closed loop poles will be the solution of As plus K times Bs equal to 0. Therefore, you can see here, if I have different value of K, then I'll have different solutions for the closed loop poles. Okay, so the open loop poles and the closed loop poles are likely to be different for different K value. Okay, open loop zeros are the same as closed loop zeros. The poles between open loop and closed loop are different. If I look at equation number 4 closely, say my K value changes from 0 to infinite. Okay, that's a whole range of values for K I'm looking at. That covers every possible closed loop pole, because if I start from, say, K equal to 0, and for every single K, I'm going to solve that equation. It will give me a pole, or a set of poles for the closed loop. If I increase the K to another value, then I need to solve that equation again, and which will give me different values for the closed loop pole. So you can see here, the closed loop poles are very much dependent on the K value we choose. Now there are 2 extreme cases. One is K equal to 0, the other one is K equal to infinite. Okay, so when K equal to 0, equation 4 becomes S equal to 0. S is equal to 0 is the same as equation number 2. So therefore, the closed loop poles will be the same as open loop poles when only and only when k equals to 0. On the other side of the extreme case, if k tends to infinite, k is very large. Now, relatively speaking, I have two terms on the left-hand side of equation 4. Relatively speaking, the second term, because k is very large, the second term will be much bigger than the first term. Therefore, approximately, we can actually neglect the first term. So the second term becomes k times bs equal to 0. Strike away the s. K is a constant. So k times bs equals to 0 is the same as bs equals to 0. Bs is equal to 0, if you look at equation 1, that's the open loop zeros. So when k is very, very large, the closed loop poles will be the same as open loop zeros. So this is really the two ends of the extreme cases. K equals to 0, closed loop poles are the same as open loop poles. When k tends to infinite, closed loop poles tend to move to open loop zeros. Okay, so what's in between are the poles for all the other possible k values. But we know the closed loop poles will start from open loop poles. As I increase k value, it will move towards open loop zeros. Okay, so the aim here is to actually work out what is in between for different value of k, but we don't want to every time derive the closed loop transfer function, solve that equation, because there are infinite number of possibilities as k has infinite number of values from 0 to infinite. So the aim is to try to work out some kind of rules to say, right, I know the closed loop poles will start from open loop poles. They will move towards open loop zeros, but can I actually find all the other possible poles in between when k has a value or has different values? Okay, so that's the rule we are trying to work out. So I'm going to work on that and look at this definition first. The RootLocus of a system is the movement of the all closed loop poles, or the solutions of the characteristic equation. That's what's in the denominator. If I just go back a few slides here, that's in the denominator of the closed loop transfer function. So if I equate this part to 0, find the solutions, these will all be my closed loop poles for different value of k. So that's the aim. We want to find all the poles or all the solutions of 1 plus kq equal to 0 as k is changed from 0 to infinite. Now look at that from a different angle. Suppose I know a complex number, or any number, or real number, or complex number. Suppose I want to know this if a particular number, S0, if that number is a possible closed loop pole, I substitute this S0 into S here, then this equation should stand. I should end up with 0 on the right hand side. Okay, if 1 plus kq S0 is not equal to 0, then this S0 will not be a possible closed loop pole, regardless of whatever k value you have. So that's really the condition we have here. Substitute S0 into qs times k plus 1. If that equals to 0, then this particular S0, which is a number, this particular S0 will be a possible closed-loop pole, and there will be a corresponding k value to make the left-hand side of equation 1 to be 0. Okay. Now think about that. This Qs is a transfer function, so it could end up with a complex number. Okay, it could be a real number, it could be a complex number. Let's say complex or real number could also be expressed in the form of a complex number. Just the initial angle would be, the phase angle would be 0. Okay, as we covered in the revision for complex numbers. So change that equation number 1 slightly in its format. So I'm going to move that 1 to the right hand side and then divide k to both sides, end up with Q S naught equals to 1 minus 1 over k. Minus 1 over k. K is between 0 and infinite. That's a positive number. Minus, in the complex plane, a real minus number means the magnitude is 1 over k. The angle is either positive 180 degrees or minus 180 degrees. Or in radians, it's minus pi or plus pi. Minus pi plus pi is the same thing. It's the same, shows, it points to the same direction. Okay, let's just say it's a minus pi for time being. Now, because it's a complex number, we treat it here. So for the S naught to be a possible closed loop pole, the open loop transfer function Qs naught should have a magnitude of 1 over k and a phase angle of minus pi. Okay, that is one of them known as the magnitude condition. The other one is known as the phase condition. Okay, so the magnitude needs to be 1 over k. Whatever k that value is, you must be able to find the value here. The other one is the phase angle of Qs, the open loop. Substitute your point into Q, then this angle should be minus pi. Now the second part, just make it cover all possibilities. This 2L pi is basically the integers of multiples of 2 pi, or multiples 360 degrees. Now it's circle, so if you go around 360 degrees, and it end up in the same position. L is any integer number. So L equals to 1, that's 2 pi. L equals to 2, that's 4 pi. 4 pi is 720 degrees. It's just going around twice, but pointing in the same direction. So we are going to rely on these two conditions. First of all, to find all the possible poles for the closed loop from open loop transfer function Qs using the phase condition. So we're going to use the phase condition first. And then once we find all the poles, all the possible poles for the closed loop system, we will use the first condition, the magnetic condition, to find the k value to move the closed loop pole to that particular point. Okay, so there are two-step process here. One is to find all possible closed loop poles, link them together. That will give us the RootLocus diagram. Any point on the RootLocus will correspond to a possible closed loop pole. If it's not on the RootLocus, then there can't be a possible closed loop pole. Okay, and then on the RootLocus, if I want the pole to be at any point, then I can use the first condition, the magnetic condition, to find the k value to get the control closed loop poles to be there. Okay, now equation number 4, 3, number 4, these are two conditions, but I need to translate that a bit more so we understand what is happening here. Okay. So to start with the phase condition, I'm just interpreting equation number 1 here, the phase condition, the phase angle of Qs must equal to minus pi plus minus 2L pi, to see how we can actually find all the possible closed loop poles. QS is open loop transfer function. Okay. Substitute S0 into here for a point to be on the RootLocus. This must stand. So I'm going to say, right, because QS equals to BS over AS, as we defined before. Now BS will have number of open loop zeros as expressed here. QS will also have the denominator term AS. If I equate that to 0, that will give me a number of poles as I expressed here. This sign here means product. So it's S minus 1 0 times S minus second 0 times S minus third 0. Equate this to 0, it will give me the notation of zeros. This sign again is a product that multiply all the different terms for different pole value or for different open loop values. Okay, so Zi here represents open loop zeros and Pi represent open loop poles. And S0 here is the one we want to try. So if S0 is part of a closed loop system, I substitute that into here, find the angle, and then I should end up with minus pi plus minus 2l pi. Now, because for the phase condition, because we are only interested in the angles, so this product, now substitute S0 into S. S0 is a complex number. Zeros are complex numbers. So this is the same as the subtract of two complex numbers. Now two complex numbers subtract will give me another complex number. Complex number will have a magnitude and phase angle. But I'm only interested in the phase angle. So I'm going to try to use the phase angles first. So this sign here indicates it's addition of all open loop zero, the angle between my point and open loop 0. This summation here indicates all the angles between my test point and open loop poles. Now, if that equals to minus pi, then I can confirm that S0, this number is a possible closed loop pole. Okay, so that's really the equation number 3. It looks complicated, but it's actually basically saying if you want to test a particular value and to see it is a possible closed loop pole, all you need to do is find the angles between this value and all open loop zeros, add them together, and then you find all the angles between this point and open loop poles, add them together. The difference between these two should be minus pi. Okay, S0 is any point that I want to try. Okay. The gain condition, that's the first condition that we use. The gain condition says, now the absolute value or the magnitude of Q open loop transfer function when I replace S by this particular value here should equal to 1 over K. In other words, K should equal to 1 over this. Now suppose K comes with number of zeros, number of poles. All we need to do is to find the distance. Find the distance between S0, the test point, and the open loop poles, multiply them together, and at the bottom we find all the distance between my test point and open loop zeros, multiply them together. Now divide this by that, or give me the corresponding K to move the closed loop pole here to S0 point. Okay, now KQ here is just a coefficient of QS, the open loop transfer function, and after you formatted it. Sometimes that's 1, sometimes it's not 1, but if it's not 1, then you have to make sure you do a 1 divided by q there. So that's really the principle of RootLocus design approach. Next time, or in the next part, I'll start to give you some examples how to actually apply these two conditions to design our control. Thank you.